Hi children, welcome back to our classes. In the last video we were discussing about electric potential and potential difference. Today we are going ahead with a calculation of electric potential. This is very interesting. Let's see that. We will calculate the electric potential due to a point charge first. We know how to calculate the electric field intensity due to that point charge. There we did that for calculating the electric field intensity of a dipole. Here also we are calculating electric potential due to a point charge. This is of course for calculating the potential of dipole and studying the concept of electric potential more. Okay, this class is very important for the exam, and we will be landing in a very important topic of this exam soon in this chapter, in this video. So listen to that. So imagine you have a point charge here. Okay, so we take it as charge Q, and we want to calculate the potential at this point, which is say R distance away. You need to calculate the potential at that point. See, potential, recollect the definition. Electric potential is the work done in bringing plus 1 coulomb charge from infinity to that point. When you are bringing that charge here, the force on that is the electric field intensity. The electric field intensity is equal to 1 by 4 pi epsilon 0 into Q divided by R square. You can recollect the formula. I hope that. Okay. Now the work done. Work done is equal to the potential is equal to, remember this. For bringing that charge to this point, you have to do work. Now this is the force when the charge is here, and when you are bringing that charge, the force is actually incrementally increasing. So the work you have to do also is increasing. So for calculating such work, we have a method in mathematics called integration. I am writing it. Just listen to that. This is how you are writing it. Okay, continuously we are doing work with a increasing force. So from integral from infinity to the point R, this is how we read it. Integrating from infinity to the point R into 1 by 4 pi epsilon 0 into Q divided by R square. This is the force, and the displacement is of course R. Okay, you are doing that. See, in integration process, we take it step by steps in small steps of dr. So this is how we write it. Okay, you will study this in detail in your mathematics classes. So once integration is taught in your mathematics classes, you can understand why this formula comes in. So for the time being, you keep it written there in your notebook. Don't worry about that, and you write the final formula. That we will by heart. Okay, this you have to by heart. It is 1 by 4 pi epsilon 0 into Q divided by R. This is the final formula. This you can guess. Here you have a force which is written like this, and a multiplication with a distance factor has to come. So that is R. So R square is converted into R. So this is the equation for electric potential at this point. I hope you got it. So you have to by heart that equation. For studying it further, what we will do is we will take an example. Just imagine the magnitude of this charge is equal to say some 10 into 10 raised to minus 9 coulomb. Very small charge. That is 10 nano coulomb. Okay, and let this distance be somewhere around 9 centimeters. That is pretty close to that charge. So you have a point charge here, this much, and we are going to calculate the electric potential at some point that is 9 centimeters away. Okay, so at this point, I write the equation for V. You may copy this into your notebook and write along with me. Okay, so it is 9 into 10 raised to 9 into Q divided by R. I hope you are writing that. This is equal to 9 into 10 raised to 9 into, here it is 10 into 10 raised to minus 9 divided by 9 into 10 raised to minus 2. Why this 10 raised to minus 2 comes in? Yes, I am converting it into the meters. So this is equal to some 10 into 10 raised to 2 volt. Okay. So this is some 1000 volts. Wow. You may wonder, such a small charge produces such a big potential. No, in fact, the electric field values and potential values are very large when you calculate it. Now, so does it mean that when you stand here you will get some difficulty? No problem. So the potential values are usually very large. Those large potentials will not harm you. We will talk about what kind of potentials will harm you in the next chapter. Okay, you have to wait till then. Now, anyhow, the idea is you have a potential of 1000 volts. Okay, you just imagine this. So if you have a charge here, okay, I draw the charge here. At a centimeter, at this distance, say 9 centimeter here, you have this much of potential. Okay, can you guess one more point with the same potential in its neighborhood? Of course, 9 centimeter to this 1000 volts means 9 centimeter, this point also will be at 1000 volts, correct, no? And if you take another point here or here, oh, that is a circle, this whole circle, okay, a circle with a radius 9 centimeter, all the points will have a potential of 1000 volts. Is there any more points? Yeah, of course there are. Now the points to this side and to that side, which are at the same distance from this charge, are also at 1000 volt. Means now you can imagine a sphere concentric with this charge with radius 9 centimeter. All those points will have this potential 1000 volts. I hope you can understand it. Correct, no? That surface, remember, a sphere concentric with this. If you change the center, if you imagine the sphere like this, it is different. Okay, a sphere concentric with this charge and a radius 9 centimeter will have a 1000 volt potential. That surface is called an equipotential surface. What is that? Equipotential surface. It's an important concept in physics. So this is an equipotential surface with a potential of 1000 volts. Got it? Can you imagine one more such equipotential surface? What is an equipotential surface? You may write the definition. An equipotential surface is a surface with the same potential on all the points. Okay. Now can you guess one more equipotential surface? You can guess. If you reduce the distance to 4.5, see, if you reduce the distance, the potential will be doubling. So here at the center point, you have an equipotential surface with 2000 volts. I hope you can understand. And if I take an 80 centimeter, if I double this distance, this is also 9. Means what? If this is 18 centimeters, this is an equipotential surface with 500 volt. Correct, no? So any number of equipotential surfaces you can imagine. See, any sphere concentric with this charge is an equipotential surface. So there are infinite number of equipotential surfaces around a point charge. You may note down that. All spheres concentric with the charge are equipotential surfaces for a point charge. Okay. And how many can be there? Infinite number. Now the concept of equipotential surface is really important. So we have already written the definition, and there are certain properties you can list for equipotential surfaces. The first property is it is a surface with the same potential all over. That's the first property. Second property is, just listen to me. Suppose you are taking a charge from this point to this point, say from A to B. You are taking a charge, you just imagine. See the equation for work done, I am recollecting from the previous class. Work W is equal to VQ. Remember, V is the potential difference. So from here to here, if you are taking a charge, V will be 0 because this point and this point are at the same potential 1000 volt. Okay. So the work done will be 0. So that is the second property. There is no work required for moving a charge on an equipotential surface. Okay. And the third property, that's again is important. Just imagine I am drawing an electric field line. So the electric field line will be like this if this is a positive charge. Remember, it is perpendicular to the equipotential surface. It will be the same in everywhere, wherever you are drawing it. That is, electric field intensity or electric field will be perpendicular to an equipotential surface. Write that also. Fourth property is, can two equipotential surfaces intersect? Suppose I am drawing one surface like this. It will have electric field intensity like this. Okay. Now, if I draw one more equipotential surface intersecting with this, it cannot be drawn perpendicular to this. That means two equipotential surfaces cannot intersect. Okay. And this property, electric field is perpendicular to equipotential surface. We will explain it a little more. Just imagine, you have an equipotential surface like this. What we said is electric field intensity must be perpendicular like this. If it is not perpendicular, what happens? It will be at an angle like this. If it is at an angle like this, it will have two components. One component in this direction and a component in this direction. If electric field intensity is like this, it will have two components. Remember, if one component is there like this, means that here electric field is there, means there is a potential difference. It cannot happen because the potential is the same all over here. So the electric field must be in such a way that it has no component along the equipotential surface. That means it should be like this. I hope that is clear to you. And little more. See, you are keeping a charge of 9 into 10 raised to minus 9 coulomb at the center. This is a positive charge we imagined. Instead of positive charge, if it is a negative charge, what change will be there? The answer is, in this equation, you have to put a minus sign for Q and the value turned out will be minus. All those values will be minus. That means a positive charge produces a positive potential and a negative charge produces a negative potential. But remember, electric potential is a scalar quantity. It is not a vector quantity. Now, this point the children often confuse. So, for understanding that, what we will do is, we will do an example. Imagine you have a charge, say 9 into 10 raised to minus 9 coulomb, as we are familiar with that. And we take this point, say 9 centimeter away. The potential is 1000 volts. Okay. So, the charge is here. It produces a potential here. Just imagine another negative charge is there. Say here. At this point, another charge, minus 9 into 10 raised to minus 9 coulomb. So that produces a potential here minus 1000 volt. Okay, is the situation clear to you? Copy that into your notebook and understand the situation carefully. This produces a positive potential here and this produces a negative potential here. So what will be the total potential? Total potential will be the sum of these two. So this is, sum will be 0. But remember, The electric field at this point, this is the point children often confuse. The electric field at this point, this produces an electric field in this direction. This produces an electric field again in that direction. So they add up. Okay. So they add up, and electric field is not 0, but the potential at that point is 0. That you should remember. See, in case if this charge, instead of being here, instead of being there, I am erasing this. Imagine that charge is here, 9 centimeter here, minus 9 into 10 raised to minus 9 coulomb. Understand this? This produces about the electric field. Both charge produces electric field there. The potential at this point, again V is equal to minus 1000 volt. V is equal to minus 1000 volt. So the total potential V total will be equal to 0. But the electric field intensity, how to calculate? This produces electric field in this direction. And what is the direction of the electric field produced by this? Okay, it is in this direction. So electric field has to be added vectorially, but the potential has to be added algebraically. This difference is there, which you have to keep in your mind. In most of the entrance examinations, this point children confuse and they produce or they have difficulty. Okay. So this point you should remember very clearly. The idea is electric field intensity is a vector, whereas electric potential is a scalar. See, for understanding another concept, we take one more example. Again, 9 into 10 raised to minus 9 coulomb charge. 9 centimeter here, I am drawing an equipotential surface. Okay, the surface potential is 1000 volt. I take double the distance. Okay, and this is a 500 volt equipotential surface. Now imagine you are taking a charge from the point A. Let the charge be equal to Q is equal to some 2 microcoulomb charge from A to the point B here. To the point B here. Have you noticed that A is on the 1000 volt surface and B is on the 500 volt surface? You have to understand this. From A to this diametrically opposite point, no work is required. Okay. So from here, let's mark that point be C. Okay. Don't confuse this C and C. Let's mark it as D. So from A to D, no work is required. From D to B, work is required. Okay. So work W is equal to, write it and solve. VQ is equal to, V is 500. The difference is 500. Remember, this V I have written is not this 500. It is 1000 minus 500. That 500 is written here. Okay. Into the charge. 2 into 10 raised to minus 6. So this much joules is the work required. And you remember, see, from here to here, no work is required. Suppose you are taking it here and see you are taking it this way, just imagine. Doesn't matter. It is not path dependent. Okay. Only the potential difference that matters. Remember this. From here to here, you can take it in any way. Any way. It is not path dependent. Okay. Here, if you are reaching the final point is here, so that is this much of work. You know, this is because electric field is a conservative field. Gravitational field was also conservative, which we studied last year. Let's quickly catch one more example. You have two sheets. If you give plus sigma here and minus sigma here, you can produce electric field inside here in this direction with value is equal to sigma by epsilon 0. You studied that. For that, what we have to do is you have to connect these sheets to a battery. Just imagine you are connecting a 10 volt battery. Just imagine. Then it is 0 potential here, 10 volt here. So electric potential progressively increases in this direction and electric field is opposite to that. So where can you expect a 5 volt equipotential surface? Now equipotential surface will be perpendicular to this. So where can you expect a 5 volt equipotential surface? Exactly in the middle. So this is an equipotential surface with 5 volt. And where can you expect an equipotential surface with 4 volt? Say it will be somewhere here. 6 volt somewhere here. Okay. So this is how they are arranged inside a 2 sheet system which is used for producing electric field. So okay, suppose the electric field you can calculate the electric field this way also. Electric field E is equal to, just imagine these are spaced say 1 millimeter apart. The 4 volt line and 5 volt surface are separated. It is minus dV by dl. This will be minus dV will be 1 volt divided by dl is 1 millimeter. So this will be minus 1 into 10 raised to 3 volt per meter. So the electric field inside you can calculate if this is correct. Okay. So the electric field will be 10 raised to 3 or 1000 volt per meter. So you have a new unit for electric field also, that is volt per meter. And this minus sign indicates that as potential increases this way, electric field is in the opposite direction. So we studied only 2 ideas today. The potential due to point charge, and we were studying about that. Then we met equipotential surfaces also. So study this carefully. There is a homework for you, problem numbers, note down. See, in the NCERT you have to solve or study and copy examples, example 1, example 2 and example 3. Okay, study that well carefully so that we can enjoy the next topic wonderfully. So with that, thank you.